My name is Tyler Bro, and this is Physics 2212 Lab 3, Magnetic Field of a Bar Magnet. We're going to start with an introduction, then go into assumption and models. We'll then compare the experimental data to the data acquired via our GlowScript coding model, and lastly, we'll cover the discussion and conclusion. The purpose of this lab was to observe magnetic fields through a visual representation, to observe the relationship between distance and magnetic field, and to use the distance dependence of magnetic fields and the Biot-Savart law to find a magnetic moment of a bar magnet. Fundamentals include the Biot-Savart law, written out here, the distance dependence formula, also written out here, and using a bar magnet to model a magnetic dipole. Preview of the results was that mu, the magnetic dipole moment, was found to be 5.365, and the value of n was negative 2.5081. Assumptions and models. The model used, we used a bar magnet to act as a magnetic dipole in order to apply the Biot-Savart law. The system would be the observation point, which would be the magnetometer, and the surroundings would be the bar magnet. Now on to the experiment. So first, we oriented our phone to be oriented with magnetic north, meaning that we found the angle at which the x value was 0. Then we found the location of the magnetometer in the phone by sliding it first oriented horizontally across the ruler and then vertically, and found the location at which the field had the strongest reading. Then the on-axis difference from the bar magnet to the magnetometer was found using the ruler for various magnetic field values. We then linearized these values by taking the natural logarithm of each side as shown below. This formula is represented on the left, and the graph plotted with this data is here on the right. Finally, the off-axis magnetic field of the bar magnet was found as shown. The phone was slid all across the horizontal ruler until the value read 100 microteslas. This distance was reported as d perp, and then we slid it upwards in the y direction, that same amount d perp, and recorded the magnetic field, the y component of the magnetic field. It was observed that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Lastly, the position of the phone matters in terms of ensuring that the magnetic field of Earth doesn't interfere with our readings for the magnetic field of the bar magnet. Calculations. The distance dependence equation was applied to find n and k. N was found to be negative 2.5081 with the logarithm equation shown in the top left. Ln of k is negative 13.745 from the same equation, which means that k is 1.703 times 10 to the negative 6th. Then the Biot-Savart law was used to find mu. Setting r equal to 1 meter and manipulating this equation a bit, shown below, it was found that the value of mu, the magnetic dipole moment, was 5.365. Comparing this to the GlowScript coding model, so mu naught over 4 pi was inputted, then a model of the magnet at the origin was created. Next, the experimental value calculated for mu is put in here. Next, a function to determine the magnetic field at a point using u and r was created. We next quickly added a scale value so that we could see these arrows in relation to our model of the magnet. And then I chose a distance of 0.241 on here. It happens to be the same as d perp, but it just made the model look nice. Then two observation axes and 4 lines were created here, perpendicular to the axis. Next, 2 arrows were created to represent the magnetic field on axis, and 4 arrows were created to represent the magnetic field perpendicular to the axis. And lastly, to visualize the magnetic field 45 degrees off axis, we inputted our experimental value for d perp and created a vector using this value. And lastly, created an arrow using our dipole b function created earlier and using r 45 degrees and our mu value to find this. And all of that came together to make this nice little model, which tells us ultimately that the magnitude of b at 45 degrees is 6.06158 times 10 to the negative 5th teslas. Compared to our experimental off-axis field value, which was 4.084 times 10 to the negative 5th teslas, you can see that there's roughly a 39% difference in the expected value and the recorded value. There's likely no discrepancies in our model, as the bar magnet very closely models that of a magnetic dipole. Some source of error could be that we had some error locating the location of our magnetometer. The initial position might not have been exactly aligned with magnetic north, and also this experiment was conducted indoors, so other magnetic fields could have been affecting our data. If the experiment was oriented to compensate for magnetic north, or if it wasn't, sorry, then we would have had to find some other way to account for the magnetic field of Earth, as it would have been affecting our values. And what if two magnets were stuck together and the end of the experiment was repeated? All of our values calculated would have been roughly doubled, as this would have made our magnetic field roughly double the strength. Conclusions are that both the Biot-Savart law and distance dependence can be applied to bar magnets with accurate results. Bar magnets can be used to accurately model magnetic dipoles, and that distance is an important factor in determining the relative strength of a magnetic field. Thank you.